Swayam Prabha. Digital India. Educated India.
Welcome to the course Geology and Soil Mechanics. So, in the last lecture we have seen the rock formation, different types of rocks, classification of rocks, and the disintegration or the weathering process of rocks, and the formation of soil and different deposits across the country. So, now we are really moving to the actual soil mechanics. So, before that we need to know different index properties of soil. So, today's lecture will be dedicated to define or to understand different index properties of soil. Now, how basically you categorize different types of soil. Now, first of all we need to discuss about the phase diagram. So, any soil if you consider, that is basically the three phase system. So, soil basically consists of soil solids, water and air. This is the general scenario in any kind of soil. So, that is why soil is known as three phase system. So, if you look at this figure, so basically if I consider this is the whole soil matrix, then part of that will be covered by soil solids and then water and then air. And on the right hand side basically we are having the weight scale, where Ws is the weight of soil solids, Ww is the weight of water, and Wa which is nothing but the weight of air, and eventually that is becoming or that can be considered as 0. Whereas on the left hand side we have the volume scale. So, total volume of the matrix is a capital V, whereas Vs is the volume of soil solids, that means this much of volume will be occupied by the soil solid particles. Then Vw is the volume of water, that will be occupied by water, and Va is the volume of air. So, that means please try to remember that Wa is 0, but Va is not 0. So, please do not do any mistake there in your consideration. So, the total weight of the matrix is capital W, which is Ws plus Ww, whereas total volume V of the matrix is Vs plus Vw plus Va. Now, where this water as well as air is getting occupied. Now, of course, when you are considering the soil, if you think about any soil matrix, basically there is there are soil solids and there will be some pore space or the void space which will be occupied by air or water or both. Now, basically this volume, this Va plus Vw, this Va plus Vw together will be conforming or will be forming the total volume of voids, that is Vv. So, total volume again is Vv plus Vs, that means volume of voids plus volume of soil solids. So, if you understand this thing properly, then rest of the things will be very simply understandable. So, this is the phase system for partially saturated. Why it is partially saturated? That means if soil is fully saturated or completely saturated, then what is happening? Soil is getting saturated by the water. So, if I say soil is fully saturated, then you do not have any air, you have only soil solids and water. So, I am considering the partially saturated, which is pretty common, which is generally common in the field. So, you have all the three components present in the soil. Now, coming to some special case where we are considering completely saturated soil, as I told you, you have only soil solids and water, whereas you can have also completely dry soil, that means there is no water at all in the matrix. that means you have soil solids and air. So, if you consider the saturated soil, then it becomes the 3-phase system becomes eventually the 2-phase system, where you have soil solids and water, and the total weight W is getting occupied by the weight of solids Ws and weight of water Ww, whereas the total volume of the matrix capital V is basically getting occupied by the volume of solids Vs and volume of water Vw. Now, if you look at completely saturated situation, now what is your volume of voids? Volume of voids is simply equal to your volume of water, because it is completely saturated, all the pore spaces or that is void spaces will be getting occupied by the water. So, there is no air at all. So, Vv will be just equal to your Vw. Similarly, if you come back to this completely dry situation, you have 2-phase system again, the soil solids and air. Again your total weight capital W will be consisting of only weight of solids. So, because we have already considered that there is no weight of what air. Similarly, if you consider the volume of total matrix, then V capital V will be consisting of Vs, that is volume of soil solids, and Va, that is volume of air. Together it will form the total volume of the matrix. Again the void space, that is all pore spaces will be occupied by air, because there is no water at all in this completely dry situation. So, Vv again will be equal to Va. So, if you understand this phase diagram, then we will be calculating different things to find out different say properties as well as different say definition which will be required to understand the soil behavior. Now, coming to some simple definitions. So, these are very much required to understand the soil mechanics, and to quantify different properties of the soil, basically you need these definitions. Now, first definition is water content. Now, what is water content? So, water content is the ratio of weight of water to the weight of solids. That means, small w is the water content is equal to Ww by Ws into 100%. It is generally expressed in percentage. So, that means it says that how much water is present in the matrix means soil matrix in comparison to the weight of solids. So, in general it can be written that small w, that is the water content, is greater than or equal to 0, since there can be no upper limit to water content, because you can have any weight of water present in the soil. So, there is no upper limit, but of course, there should be a lower limit, that is 0. So, maximum or at the minimum what you can have? You can have the 2-phase system which is completely dry. So, there is no water at all. So, W is completely equal to 0. So, that situation exists, but there is no upper limit for the water content. Now, second definition is the void ratio. So, these definitions, please I request you all, please try to remember these definitions or understand these definitions, because these definitions will be frequently used in the whole course whatever we will be learning in this particular subject. Well, so coming to the void ratio. So, void ratio is generally expressed as small e, which is nothing but equal to Vv by Vs. What is Vv? Volume of voids, and what is Vs? Volume of solids. That means, this is the ratio of volume of voids to the volume of solids. So, in general E greater than 0, of course, E should be greater than 0, because E cannot be equal to 0, because your Vv cannot be 0 simply. So, any soil matrix if you consider, you should have some Vv. So, if you have some Vv, so E must be greater than 0. Since a soil has to contain some voids, it is obvious, it is quite obvious, you cannot have any soil matrix which is voidless. Okay? So, since a soil has to contain some voids, but there cannot be an upper limit to the void volume. So, because the soil has to contain some voids, so E must be greater than 0, E cannot be equal to 0, and there cannot be any upper limit. So, volume of voids could be anything. So, if it is very densely packed, then volume of voids will be less. If it is very loosely packed, then your volume of voids will be more. It depends on how the matrix is getting formed. Then coming to the porosity. So, porosity is generally expressed in terms of N, which is equal to VV by V, that is the total volume. That means the ratio of volume of voids to the volume of total soil matrix, and it is also expressed in percentage. So, the porosity cannot exceed 100%, please remember. So, this is the difference between porosity and the void ratio, where void ratio was not having any upper limit, whereas the porosity is having the upper limit, that is 100%. Why it is so? If you look at the equation or the expression, VV at the most can be equal to V, right. So, V is the total volume. So, if I consider, hypothetically, if I consider the total volume of the soil matrix is occupied by the total void space. So, that means there is no solid at all, okay, or even if there is some solid particles, they are negligible in terms in comparison to the total volume of the matrix. So, in that situation your porosity must be equal to 100%. So, but that is the upper limit, it cannot go beyond 100%. So, thus it can be 0, N should be greater than 0, okay, of course, because no soil can have 0 void space or the 0 void volume. So, N must be greater than 0, but should be less than 100. Then coming to the degree of saturation. So, degree of saturation is expressed by the ratio of volume of water to the volume of voids into 100, that means again it is expressed in percentage. Now, what does it mean? What do you mean by degree of saturation physically? Say suppose you have the voids. Now, if I say this soil is 10% saturated, or the degree of saturation of this soil is say 10%, or degree of saturation of this soil is 30%. So, what does it mean basically? That means you have the voids, and these voids will be occupied by either water or air. Now, if the void is getting occupied by water more, then your degree of saturation will be automatically increasing. So, that is the idea, or that basically that indication you will be getting from your degree of saturation value. That means how much void space is getting saturated by the water. So, VW by VV. So, S varies between 0% and 100%, of course that is true, because at the most you can have VW equal to 0, that means completely dry situation, that is again also two phase system. So, you have soil solid particles and you have air. So, there is no water. So, in that situation your degree of saturation is equal to 0, simply 0. And if you consider fully saturated soil where you do not have any air, then your VW becomes equal to VV, as we have seen in the phase diagram. So, your S becomes 100%. Now, coming to the another definition, air content, AC is defined by VA by VV, which is nothing but 1 minus S from the definition. Now, S is nothing but your degree of saturation. Now, coming to the another definition, percentage of air voids, that means how much air is present in comparison to the total volume of the matrix. So, that is nothing but the ratio of VA to the total volume V, and it is also expressed in percentage. Then coming to the bulk unit weight. Now, we are coming to very important definition, that is bulk unit weight, that is nothing but the total weight of soil mass W, okay, which is nothing but equal to Ws plus Ww if water is present. If water is not present, only Ws per unit volume V. So, unit volume means the total volume of the matrix soil whole system. So, gamma in some books you will be seeing gamma T, or some books you will be seeing gamma B. So, I am writing both the things. So, gamma T or gamma B is equal to W by V, which is nothing but equal to Ws plus Ww divided by all volumes Vs plus Vw plus Va. Now, coming to the next definition, dry unit weight. Now, what do you mean by dry unit weight? Dry unit weight is expressed as gamma D, which is equal to Ws by V. That means the weight of solids, weight of soil solids by the total volume of the matrix. Now, what does it indicate? Why do we really need this dry unit weight? Because already we have defined some unit weight, bulk unit weight. Now, why do we need that? So, gamma D is used as a measure of the denseness of a soil. Then if your gamma D is increasing, then you can say, or your indication should be, we are going to more dense deposition of the soil. That means if gamma D increases, that means weight of solids is increasing for a particular value of volume of total matrix. So, a high value of gamma D indicates that more solids are packed in a unit volume of the soil, right, and hence a more compact soil. So, that means if gamma D increases, you will be getting more compactness or more denseness in the soil matrix. Then coming to the saturated unit weight. Now, saturated unit weight, when I am talking about, this is nothing but the bulk unit weight. I mean, we are defining this thing in little bit different way to differentiate from the bulk unit weight. This is nothing but the bulk unit weight of the soil when it is completely saturated. So, if you see the expression gamma sat is equal to W saturated W sat by V. So, it is very similar to the bulk unit weight expression, only thing is that we are talking, or we are taking the weight of saturated soil. Then submerged unit weight. Now, why do we need this submerged unit weight? Suppose if you consider water table, I mean you know the water table, right, for any kind of tube well construction or any kind of well construction, you need to have the idea for water table. Now, if you consider the soil below the water table, then of course soil will be experiencing some buoyancy force, and because of that you will be getting some reduction in the unit weight, as you know from the law of Archimedes. So, the submerged unit weight is very important when you are drilling the soil below the water table. That means it is completely submerged, filled with water, water table is on the higher side. So, because of the submergence you will be getting some reduction. What is the reduction? So, gamma submerged is generally expressed as gamma prime is equal to W submerged by V, which is equal to gamma sat, that is whatever we have seen, gamma saturated, gamma sat minus gamma W, where gamma W is the unit weight of water. So, when a soil mass is submerged below the groundwater table, a buoyant force acts on the soil solids, which is equal in magnitude to the weight of water displaced by the solids, which is coming from the physics. So, there is no issue for that. So, the net weight of solids is reduced. So, if you do not consider this, if you consider the bulk unit weight even below the groundwater table, then your design is wrong. So, you need to consider the submerged unit weight, which will be giving you the actual picture below the groundwater table. Then unit weight of solids, only solids. If we are considering only soil solids, then what should be the unit weight? So, that is defined by gamma S, which is equal to Ws by Vs. Then specific gravity of solids defined by Gs. So, Gs is defined as a ratio of the weight of a given volume of solids to the weight of an equivalent volume of water at 4 degrees centigrade. So, if your water is at different temperature, then you need to, of course, you need to provide some correction. Otherwise, by and large we generally consider that Gs is equal to Ws by Vs into gamma W. That is, Gs is equal to gamma S by gamma W, where gamma S already you have seen, gamma S is the unit weight of solids and gamma W is the unit weight of water. So, the value of Gs, that is specific gravity of solids, for a majority of soil lies between 2.65 and 2.8. So, whatever soil you generally take, it lies between 2.65 to 2.8. So, this is a very typical property of soil. Now, we are talking about the classification of soil. Say we need to classify of the soil. Say, I mean, you all know that from, I mean, without knowing this subject, you know what is sand and what is clay. So, if I give you some soil specimen, then by seeing the specimen, you will say, okay, this is sand, this is clay, this is gravel, this is boulder. So, something like that. But those are the things. Now, if I ask you, okay, this is, you are telling this is sand. Now, what type of sand? It is coarse sand or medium sand or fine sand. So, for that you need some quantification, you need some classification. Now, if I say, you are saying this is clay, whether it is really clay or silt. So, for that you need some quantification. So, to quantify those things, to understand this thing in a better way, you need to classify the soil. For that you need to perform some test, laboratory experiments. So, the tests carried out in order to classify a soil are termed as classification tests. The numerical results obtained on the basis of such tests are termed as index properties of soils. Now, basically when you are classifying the soil and different numerical results, numerical values, we will be seeing those things later on in the subsequent lecture, different numerical terms, numerical parameters you will be observing, and all those numerical parameters will be known as index properties of soil. So, suppose if I tell these are the index properties of this type of soil, a person sitting in outside or sitting in anywhere in the world will understand, okay, what type of soil I really mean for. Now, grain size analysis of coarse grained soils is carried out by sieve analysis. So, we will be having a stack of sieves, and that sieve analysis will find out the gradation or the grain size analysis for the coarse grained soil. Coarse grain means, suppose you have boulder, cobbles, then sand. So, those things are known as coarse grained soil, whereas fine grained soil are analyzed by the hydrometer or the pipette method. So, fine grained soil means clay, which you cannot see from your by your bare eyes, right. So, those soils will be defined as fine grained soil. So, for fine grained soil classification you need hydrometer test. In general, as most soils contain both coarse and fine grained constituents, it is obvious, as you know, that if I give you the soil, you will be getting some percentage of sand mixed in that, you will be getting some percentage of clay mixed in that. So, it is a mix of coarse grained and fine grained. Then if I ask you to classify that thing, then you should have some proper process or proper say method by which you can classify them. Now, a combined analysis is usually carried out, where a soil sample in the dry state is first subjected to sieve analysis, and then the fine fraction is analyzed by the hydrometer or pipette method. That is quite obvious, because I mean already we have decided that the sieve analysis will be done to classify the coarse grained soil, and hydrometer analysis will be done to classify the fine grained soil. Now, if you have the mixed property or the mixed population in the matrix, then you need to perform both the tests to classify the whole range of the soil particles. So, that is there. So, in the dry state you will be doing the sieve analysis, and then the hydrometer test, basically you cannot do the dry analysis, you have to go for the wet analysis. Now, according to basically we are going to talk about the sieve analysis. So, according it is now we will be talking about as per IS 460 1962 revised. So, sieves vary in size from 80 millimeter to 75 micron. The representative sample is separated into two fractions by sieving through the 4.75 millimeter IS sieve. The fraction retained on 4.75 millimeter sieve is called the gravel fraction, which is subjected to coarse sieve analysis. So, you will be having in the sieve analysis system, you will be having two different sieve analysis, one is coarse sieve analysis, another one is fine sieve analysis. The coarse sieve analysis will be done for the gravel fraction, which will be retained on 4.75 millimeter sieve. a set of sieves of size 80 millimeter, 20 millimeter, 10 millimeter and 4.7 millimeter is required for further fractioning of gravel fraction. So, you will be having the stack of different sieves as I told you 80 millimeter on the top, then 20 millimeter, then 10 millimeter, then 4.75 millimeter, and then you will be putting the gravel fraction on top of the sieve and then you shake it, and each sieve will be retaining some amount of particle, and based on that you just classify. Okay. So, we will stop here today. So, in the next class we will be discussing about how to perform different sieve analysis. Thank you very much.